So I'd like to try an application of our probabilistic interpretation of the absolute value of the wave function squared and do a simple calculation which sort of shows the method. So for this particular example, we'll ask the question, what's the probability of finding a particle in a box where the box goes from 0 to L to be in the specific interval or subinterval to be in 0 to L over 4 if the particle happens to be in the ground state? Classically, of course, the particle just oscillates around and sloshes around in the box, and so the probability of being in a particular part of the box or quadrant of the box would just be 25%. But in quantum mechanics, we will find a somewhat different answer. So what we're looking at is this. This is the potential. It goes to infinity at L. It goes to infinity at 0. Outside of this box, psi is 0. Psi is 0. This is the n equals 1 state, so if we were to graph psi, it looks like that. It happens to correspond to the case of k sub n, where n is 1, to be just pi over L. So remember, k sub n for the particle in the box solution is n pi over L. We're just going to substitute n as 1. So for this ground state wave function, psi looks something like this. Psi 1 of x is a constant a, sine pi x over L. Remember that a is the square root of 2 over L. So how do we solve this problem then? The specific computation that we need to do is to evaluate the probability to be within the interval 0 to L over 4 psi of x squared dx. That's the answer that we're going to seek. Well, now we're going to plug in our expression for psi of x. So I integrate from 0 to L over 4, a squared sine squared of pi x over L dx. And at this point, it's useful to do a substitution of variables. We will define u as pi x over L, du as pi dx over L, in which case our integral can be simplified just a little bit. I'm going to substitute in for a squared, that's 2 over L. Instead of the integral going from 0 to L over 4, it's going to go, for x, it's going to go from 0 to pi over 4 for du. So that's my integral once I've done that substitution of variables. Now, it's a little difficult. Oh, I'm sorry, I forgot to multiply by the extra factor of L over pi, because I switched from dx over to du. So in this case, the L's will cancel. And I should point out that it's a little difficult to integrate just sine squared of a function, or sine squared of u. So it's advantageous to do a trig substitution here. And instead of integrating sine squared u, I'm going to use the identity that cosine of 2u is related to sine squared of u. So sine squared is equal to 1/2 of 1 minus cosine of 2u. And now I notice that the 2's will cancel. And I have the following expression. So I have 1 over pi. This integral is just u. I'm going to evaluate it pi over 4 and it's 0. That gives me just pi over 4. The antiderivative of cosine of 2u is 1/2 sine of 2u. I'm going to evaluate that at pi over 4 and at 0. and this is 1 over pi, pi over 4 minus, let's see, I have sine of 2 times pi over 4, that's sine of pi over 2, and that's 1. And if I evaluate it 0, of course, sine of 0 is 0. So notice that the probability is 1/4 minus a little bit, minus 1 over 2 pi. So that comes out to be, well, it's not such a little bit. It comes out to be a probability about 0.09. Again, classically, if the particle was just bound in a box and could be anywhere of uniform probability, that our answer should have been 25%. But it's the fact that the probability distribution is so peaked toward the middle for the ground state that this piece of the integral then works out to be relatively small compared to that piece of the integral. So this is an example of how to do a computation solving for the probability of a particle being within a certain subinterval.